Chemical reaction. Chemical reaction, a process in which one or more substances, the reactants, and converted to one or more different substances, the products. Substances are either chemical elements or compounds. A chemical reaction rearranges the constituent atoms of the reactants to create different substances as products. Chemical reactions are an integral part of technology, of culture, and indeed of life itself. Burning fuels, smelting iron, making glass and pottery, brewing paper, brewing beer, and making wine and cheese are among many examples of activities incorporating chemical reactions that have been known and used for thousands of years. Chemical reactions abound in the geology of Earth, in the atmosphere and oceans, and in a vast array of complicated processes that occur in all living systems. Chemical reactions must be distinguished from physical changes. Physical changes include changes of state such as ice melting to water and water evaporating to vapor. If a physical change occurs, the physical properties of a substance will change, but its chemical identity will remain the same, no matter what its physical state. Water or H2O is the same compound, with each molecule composed of 2 atoms of hydrogen and 1 atom of oxygen. However, if water as ice, liquid, and vapor encounters sodium metal or Na, the atoms will be redistributed to give the new substances molecular hydrogen or H2 and sodium hydroxide or NaOH. By this, we know that a chemical change or reaction has occurred. The concept of a chemical reaction dates back about 250 years. It had its origins in early experiments that classified substances as elements and compounds, and in theories that explained these processes. Development of the concept of a chemical reaction had a primary role in defining the science of chemistry as it is known today. The first substantive studies in this area were on gases. The identification of oxygen in the 18th century by Swedish chemist Carl Wilhelm Scheele and English clergyman Joseph Priestley had particular significance. The influence of French chemist Antoine Laurent Lavoisier was especially notable in that his insights confirmed the importance of quantitative measurements of chemical processes. In his book, identified 33 elements, substances not broken down into simpler entities. Among his many discoveries, Lavoisier accurately measured the weight gain when elements were oxidized, and thus ascribed the result to the combining of the element with oxygen. The concept of chemical reaction involves the combination of elements clearly emerged from his writing, and his approach led others to pursue experimental chemistry as a quantitative science. The other occurrence of historical significance concerning chemical reactions was the development of atomic theory. For this, much credit goes to English chemist John Dalton, who postulated his atomic theory early in the 19th century. Dalton maintained that matter is composed of small, invisible particles, that the particles or atoms of each element were unique, and that chemical reactions were involved in rearranging atoms to form new substances. This view of chemical reactions accurately defines the current of subject. Dalton's theory provided a basis for understanding the results of earlier experimentalists, including the law of conservation of matter, or matter is neither created nor destroyed, and the law of constant composition, or all samples of a substance have identical elemental compositions. Thus, experiment and theory, the two cornerstones of chemical science in the modern world, together define the concept of chemical reactions. Today, experimental chemistry provides innumerable examples, and theoretical chemistry allows an understanding of their meaning. In reactions under normal laboratory conditions, matter is neither created nor destroyed, and elements are not transformed into other elements. Therefore, equations depicting reactions must be balanced. That is, the same number of atoms of each kind must appear on opposite sides of the equation. The balance equation for the iron-sulfur reaction shows that one iron atom can react with one sulfur atom to give one formula unit of iron sulfide. Chemists originally worked with weighable quantities of elements and compounds. For example, in the iron-sulfur equation, the symbol Fe represents 55.845 grams of iron represents 32.66 grams of sulfur, and FAS represents 87.911 grams of iron sulfide, because matter is not created or destroyed in a chemical reaction. The total mass of reactants is the same as the total mass of products. If some other amount of iron is used, say 1/10 as much, or 585 grams, only 1/10 as much sulfur can be consumed. The only 1/10 as much iron sulfide is produced 8.791 grams. If 32.66 grams of sulfur were initially present with 5.585 grams of iron, then 28.859 grams of sulfur would be left over when the reaction was complete. A chemical reaction will favor the formation of products if the sum of the changes in entropy for the reaction system and its surrounding is positive. An example is burning wood. Wood has a low entropy. When wood burns, it produces ash as well as high entropy substances, carbon dioxide gas, and water vapor. The entropy of the reacting system increases during combustions. Just as important, the heat energy transferred by the combustion to its surroundings increases the entropy in the surroundings. The total of entropy changes for the substances in the reaction and the surroundings is positive, and the reaction is product favored. When hydrogen and oxygen react to form water, the entropy of the products is less than that of reactants. Offsetting this decrease in entropy, however, is the increase in entropy of the surroundings owing to the heat transferred to it by the exothermic reaction. Again, because of the overall increase in entropy, the combustion of hydrogen is product favored.